Hello grade 12s, this is physical science. My name is Gillian, and what we're going to do today is we're going to consolidate our knowledge of electrodynamics. Now, a vast subject, I know, and lots of brain work that we have to do, but let's have a look at one type of question we could get that's really asking us to give knowledge from different areas within the electrodynamic topic. So this first question says, a simplified diagram of an electrical machine is shown below. Now, I want you to have a look at this quite carefully, and we're going to unpack it and draw on it and write around it what we know. So if we look at this picture, we can see we have got a north there and a south there. So we've got a permanent magnet, and so we could draw in some field lines, magnetic field lines, and we know that they go from north to south. The second thing we notice here is that we have a circuit. So have a look there, there's a cell, we have a circuit, so there's an external circuit connected to this coil, and they tell us that the coil is this piece of wire thing inside the magnetic field. There is a positive side to our cell, and there is a negative side. When we're dealing with electrodynamics, we are talking about conventional current. So we're talking about the flow of positives or positive charge. So it will move from the positive terminal of the cell to the negative terminal. So we can draw in an arrow showing that the current, the conventional current, is flowing from the positive all the way through. It's going to flow this direction as well in the coil, along the back, you can see there, and then back through the second half of the coil and out to the negative terminal. This weird looking thing here is either going to be a split ring commutator, I've written them up there, or it's going to be two slip rings. So we need to decide which one it is. So let's see what the question is asking of us. 1.1.1 says, is this machine a DC motor? Okay, so it's direct current, or a DC generator. Okay, so the motor is the one which has electricity moving through it. It's connected to an external circuit. And the generator is the one where we have induced current as a product of that interaction. Okay, so which one do you think it's going to be? If we look at the diagram, we can see that it has got an external circuit. It has got a supply of current. It has a supply of potential difference, and so the answer here is going to be a DC motor. That's what this machine is, because electricity in external circuit is providing the current through to the coil. Write down the energy conversion that takes place while this machine is in operation. So let's think about that. We are not having to move the machine. Okay, so that's not mechanical energy. What does it start with? It starts with electrical energy. So electrical energy, how do I know that? Because I have a power supply. So, So the energy supply that's going to happen, or the energy conversion that's going to happen, is going to be an electrical energy is being transformed into a mechanical energy. Now mechanical because the coil is going to move as a result of the current interacting with the permanent magnetic field. So mechanical energy is the result of this interaction, a movement. Our next question says, write down the name of component A, and then they show us their component A in the diagram. So remember right at the beginning, it can be one of two things. So if you look at this, you can see it is a cylinder that has been cut so that there are gaps, and there's only, in total, there's only one ring. They're not two rings. So the two names that we had was a split ring commutator or a slip ring. So this is the split, it's cut in half, and so it is going to be the split ring commutator. And that component allows the current to stop flowing in the coil for a very brief moment to allow the coil to flip over, to carry on moving, and the current then changes direction within that coil. So it enables the coil to move continuously in the same direction. Now 1.1.4 says, in which direction will the coil shown in the diagram above rotate? Choose from clockwise or anti-clockwise. So we need to know some things before we can answer this. The first is, which way is the permanent magnetic field lying? So here we have, in this picture, we're going to draw it in again. We have the permanent magnetic field, and it is from north to south. We've ascertained that. Now, we are talking about conventional current from the positive terminal to the negative terminal. We have to identify the positive terminal and the negative terminal, and so the flow of current is going to be in that direction, and in the other side of the coil, it's going to come up this way. Once we've done that, we need to decide which rule we're going to use to figure this out. So we have one which is a universal, and that is the right-hand slap rule. We could use that, or we could use the left-hand Fleming motor rule. Okay, now why I choose that is because it tells me it's the motor rule. The word Fleming, okay, helps me with which hand it is. So we've got an L and an E in that word, and so that tells me that it's the left hand that I need to use. I'm going to start off using this one. So the left-hand Fleming rule, it's a motor rule. What are these fingers doing? Well, this finger, my first finger, is from the knuckle to the tip, is telling me the direction of the magnetic field. My second finger is showing me the direction of the current. And then my thumb tells me the force, what's happening, which direction is the movement happening. So the question is asking in which direction is this coil going to move. So I have to figure out the thumb. Which way is that going to be pointing? So let me set it up. From north to south, that is the direction of the magnetic field. Now I can choose. I can choose which side of the coil I'm going to use. For me, if I look at this, it is easier for me to use the side of the coil that's over here. I just want to change the color of my pen so that you can see what I am showing you. So here, this side of the coil, if we try and use both sides, it's just going to be confusing. We have to choose which side you want to use. So I'm choosing that one because it's easier for me. Because here's my second finger. It is from my knuckle to the tip, and it's pointing in the direction that the current is moving. So I can see it's moving towards me, it's into me. I can put the direction of my magnetic field from my knuckle to the tip, north to south. And then my thumb points upwards, and that tells me that this side of the coil is going to move upwards. What is going to happen to the other side? I can check it out using this rule as well. Let's see, it's going to be a bit awkward, but I will try. So if I do that, turn it around, you can see that the current is moving away from me, that the field is still from my knuckle to the tip of my finger, and my thumb is pointing down. So this side of the coil is going to go down. So which way is this particular coil moving? Well, it's moving in this direction, which is in an anti-clockwise direction, and so that is going to be the answer. Anti-clockwise. It's quite a lot of work, mental work to do to get this answer. You need to be able to use your fingers and your hands in the correct way, the correct rule to use. You can obviously use the right hand slap rule, and maybe you can take a break now and try it out using the right hand slap rule just to check that my answer is correct. Right, grade 12s, we'll see you in a moment. Welcome back, grade 12s. We're busy with consolidation of electrodynamics, talking about machines and how they work. We are now going to look at a question which involves calculation and how we process that, what equations we need to use, and how we're going to substitute values into those equations. So this question is giving us an electrical device, and it has a marking on it. So the marking on this electrical device is 200 watt and 220 volts. Now, when we have appliances that we're using, although it gives us these values, they are average values, because our electrical current that comes through the sockets in the wall is alternating current. It has highs and it's got lows, so it's got a maximum and it's got a trough, it's got a minimum, and we have change in direction, and so we cannot use very specific values of current and potential difference. And potential difference goes hand in hand with current because of Ohm's law. We know that as we increase the one, the other one's going to increase. Decrease the one, the other one will decrease. So we have to use averages for these values. So this value that is given to you is 200 watt. That is actually average power. And we write it like this, P average. Okay, the same applies for this potential difference, the voltage. It is an average. Now, if you remember correctly, that we have these RMS, which is telling us that that is the average potential difference for that particular electrical device. The first question is define the term RMS voltage. RMS voltage, it's the average, right? So this is something that you would need to learn off by heart. And so let's look at this answer. The AC voltage, you can either use the word voltage or you can use the word potential difference, which dissipates the same amount of energy or heat or power as an equivalent DC, look there, DC voltage or potential difference. So it's an average. So this potential difference is an average, and they're saying that the AC potential difference is the same amount of energy that is given or dissipated as an equivalent amount of potential difference, that's DC, direct current. Okay, so these are the words: AC, alternating current, and DC, direct current. Something you just have to learn. Our next question is asking us about calculating. So calculate the resistance of this device. So I'm going to write our values down again. So we've got P average, power average was 200 watt, and the potential difference, the average potential difference is 220 volt. We have a number of options. We've got to try and find the resistance of this appliance. We have another number of options. We've got the average power is equal to the average current times the average potential difference. We've got this equation here, which is I squared times R, and we've got this one here, which is V squared divided by R. Now, I would not want to choose this equation or this one. Why? Well, I'm not given the I value, the current value. I'm given VRMS, and I've given P average, but I'm really not given I, the value of current. So if I choose these two equations to use, I would have to do a second step in my calculation. It would make sense for me to use this formula rather. And I write it out like that. So P average equals square of V, but it's not just V, it's RMS divided by R. I substitute in my values, I get 200 equal to 220 squared divided by R. And once I have worked that out, I end up with an answer of 242 ohms. I just want to go back to this. If you choose to use one of these two formulae, you will have to calculate what I is first, and then from that you would substitute it in to find the R. This device now, this that we've just worked out, is connected to an AC source of 150 volts. Calculate the energy dissipated by the device in 10 minutes. So energy dissipated or energy transformed is the same as work done. Work done. Okay. They give me a value for time which is 10 minutes. If you remember back, work done or energy dissipated the unit is joules per second. So when I'm working with these values, I have to convert the minutes into seconds. And so we do that by saying 10 times 60. This formula is the one that I would choose to use because it really doesn't involve a lot of calculation. There are others that you can use. I've just changed my screen to show you. There are others that you can use. But this one for me makes more sense because I do not have to do a second step in the calculation. So work done or energy transferred, dissipated, is equal to the potential difference of this AC source, which is 150 volt. It is squared. What is my change in time? Well, it's from T0 to 10 minutes, and I have to change the 10 minutes into seconds. So I times that by 60. 10 by 60, and I need to then substitute in the value for R, which is the resistance, and we found that to be 242 ohm. So I'm going to put that in, 242 ohm, and then I can calculate my answer. What happens if you choose a different formula? So I have this formula that I could use where I find out the power. So I calculate the power using V squared RMS over R. So the V we know is 150 square divided by 242 ohm. And then I get an answer of 92,975 watt. That still isn't giving me what is being asked. I'm being asked about the energy dissipating. Power is the rate at which energy dissipates. So when we're talking about a rate, we're talking about time. So this formula here tells me everything about power. It's saying that it's energy dissipated or work done per unit time. That gives me the rate. So I have to take this answer of power, the average power, and I have to substitute it in again. So I get power, which is 92, that I have just calculated. Energy dissipated is what I want to find, and the change in time is 10 minutes times 60, converting it to seconds. And once I've calculated that, I will get my answer. Right, grade 12s. I hope that has helped you with how to use your data sheet, the formula. I want to reiterate that when you are writing out these formula from the data sheet, you have to write RMS if you are using the average potential difference or the average current. So I'm going to write it up here. So if you are using the average current, you need to write in your formula RMS. And if you are using the average potential difference, you need to write RMS next to it there. Power is average power because we're not working on specific maximum values. We're looking at the average overall of the current that is changing in strength and in direction continuously. Good luck with working through these examples. The answers will be available to you to look at and to mark. Have a good one, grade 12s.